Okay, I'd like to draw a hybrid orbital diagram in this video, and we're going to start off with a fairly simple example to kind of drill the foundations of these diagrams, as they can be a little bit tricky for some students. So we're going to start off with a molecule called ethylene. Ethylene is a carbon-carbon double bond. Now, carbon requires 4 bonds to have a formal charge of 0, so each of these carbons will have 2 hydrogens coming off of it. And before we get to drawing the diagram itself, I want to point out a couple things. You always want to identify the hybridization of the atoms involved in the hybrid orbital diagram before you start drawing it. Now, this is a symmetric molecule. It has a plane of symmetry, so each of the carbons will have the same hybridization, and the hybridization of each carbon is sp2. We know it's sp2 because each carbon has 3 regions of electron density. If you're still not comfortable assigning hybridization to atoms, I would review the notes on that. A couple other things. Because it's sp2 hybridized, the bond angles here are going to be 120 degrees because we have a trigonal planar geometry. Whoops. So you do want to account for those bond angles when you're drawing the hybrid orbital diagram. Now, it doesn't have to be exact. Nobody's going to take a protractor to your diagram, but they should be relatively, on par with what 120 degrees would look like in the plane. Also, this carbon-carbon double bond is a result of a sigma and a pi bond overlapping. That's going to be important to show in the diagram too. And one last thing, each of these carbons has a unhybridized p orbital, and we'll account for those unhybridized p orbitals in our diagram as well. All right, so we can start drawing the diagram, and the first thing I'm going to do is draw in my carbons. Hopefully no shock there. And then I will now draw in the sp2 orbitals of each carbon. Each carbon has 3 sp2 orbitals. Okay, I'll label these as sp2 now. And we've now formed half of our double bond here. We formed the sigma bond, so we will show the sharing of electrons as well. Okay, next up, I'm going to draw in the hydrogens, and each hydrogen brings a s orbital with it because hydrogen has only an s orbital. So we're going to show the s orbitals here, overlapping with each of the carbon's sp2 orbitals. And I'll label these as 1s and hydrogen. And we've formed a sigma bond in each of these cases, so we're going to draw in our electrons and label them as a sigma bond. All right, next thing is kind of a part that students will forget about often, and that's the fact that each of these carbons, sp2 orbitals, has a back lobe to it. Now, the back lobe is a result of constructive and destructive interference of the atomic orbitals. That goes back to molecular orbital theory, and the exact reasoning behind why we have a back lobe is not important for the purposes of this course, but you do need to show the back lobe, and I'm going to represent the back lobe of each of these carbons as just 3 little circles. Some people will kind of dash them or fill them in, and I don't do that because I save the wedging and the dashing for showing the orientation of things in the hybrid orbital diagram, and I think it can get confusing if you shade things in. All right, now the last part we have to show is actually one of the most important parts, and it's a part that students often have trouble with, and that's representing that each of these carbons has an unhybridized p orbital. Now remember, a p orbital has 2 lobes, a lobe coming towards you and a lobe coming away from you. So you need to show the orientation of each lobe in your diagram via wedging and dashing. So I'll show the unhybridized p orbital on this carbon first by drawing a lobe coming towards me, and then by drawing a lobe coming away from me. Actually, that's not really as big as I wanted it to be. Notice the wedging and dashing. The wedging indicates it's coming towards me, the dashing away from me. And this is a single unhybridized p orbital. It just has 2 lobes, remember that. And it's pz because that is the only unhybridized orbital that remains. P orbitals consist of an x, y, and z axis. And we have sp2 orbitals in the x and y direction as of now. So the unhybridized p orbital would remain in that z direction. And I'll draw the unhybridized p orbital on this carbon as well, first by drawing one lobe coming towards me and one lobe going away from me. And the one last thing I need to show is the fact that we already have our sigma bond, and the one last part remaining of that sigma bond is the pi bond. So these two unhybridized p orbitals will overlap to form the pi bond. Because there's 2 lobes in each unhybridized p orbital, 2 lobes will overlap to form half of the pi bond, and the other 2 lobes will overlap to form the other half of the pi bond. And both lobes overlapping will form that single pi bond. So we show that kind of half sharing of electrons via half of the p orbitals sharing 1/2 of the electrons, and the other 2 lobes sharing the other half of the electrons. And this is the complete hybrid orbital diagram for ethylene.